Question 9. If a baseball pitcher threw a baseball straight up, how high would we be able to throw it? So, although somewhat artificially, he certainly wouldn't be able to throw it as high as he could pitching it, but let's just imagine that I'm simply asking if I throw a baseball up in the air, and let's imagine that I can throw it at 100 miles an hour. That's probably about, let's say 30 meters per second. Okay, so 30 meters per second. I throw it up in the air. Pretty much, I want to know how high it goes. So the easiest way to do that is simply look at kinetic energy, gravitational energy. At the bottom, it's 0 here. It's 1/2. Let's say the baseball is a third of a kilogram. So a third of a kilogram times 30 meters per second squared. Okay? At the very top, I have no kinetic energy, and I have a third of a kilogram times 10 joules per kilogram meter times the height. Okay, so what this does then is, so this gives me a total energy. So I have no gravitational energy here. I can figure this out. 30 squared is about 1,000 divided by 6 or so gives me about 200 or so joules. So let's say it's 200 joules just for round numbers. I go up here. I set this equal to 200 joules. And then I can get a height 6, so this gets me about 60 meters. Okay, so I solve for the height. Now, the question then becomes, if the ball were twice as heavy, how much would this affect the speed of the pitch? And pretty much what we're doing is we're saying, if we increase the mass by a factor of 2, what will happen? Now, I think it's pretty clear that the pitcher will not be able to throw the baseball quite as quickly. So what is constant between those two things? And one I think reasonable assumption is that he provides the same amount of energy, same amount of kinetic energy to both balls. So what we have is we have our initial situation where essentially we have 200 joules, but instead of so I have 200 joules, and now I have something that is, instead of a third of a kilogram, we have 2/3 of a kilogram. Okay, so that's gotten up by a factor of 2, and then I have a v squared, and then I can bring everything over. What we'll find is that the speed. So what will happen is, because now the mass has gone up by a factor of 2, and the speed, but the kinetic energy is the same. This implies that the speed must go down by the square root of 2, or by like 1.14, and you'd find that by just simply running the numbers. Again, doing that. Now, the next thing, with the twice as heavy ball, how much lower would the ball reach if it pitched straight up? So again, we have 200 joules. 200 joules of energy gave me 60 meters. If I increase the mass by a factor of 2, that will simply go down by the factor of 2. So this will go down by a factor of 2. So it's because the speed comes in squared and the kinetic energy goes down by a factor of 1 over square root of 2. Because the height comes in linearly in the energy, it goes down by a factor of 2. And you could just simply figure out how many joules and then just run the numbers in each case, and it would show it and then you could show it in general. If you just give it, you could also do it simply by saying we have 1/2 mv squared is equal to m times g, which is that 10 meters per second squared, or 10 joules per kilogram meter. That's what that G is. And notice the mass in this case cancels, and then we can get a general equation. But then when I say 1/2 m1 v1 squared is equal to 1/2 m, like 2m1, so I've replaced the mass with twice the mass, v2 squared. How does v2 compare to v1? And again, it goes down. v2, as you can immediately see, v1 squared is equal to 2 v2 squared, or v1 is equal to the square root of 2 times v2, or v2. So v1 is larger by a factor of square root of 2 than v2. So you can do it that way, somewhat more generally than you would otherwise, or you can run the numbers.